All right, so in this part of Chapter 13.3, we'll look at factors that affect solubility. What makes things dissolve in other things? The general rule is that like dissolves like. So polar things dissolve polar things, non-polar things dissolve non-polar things. This is true because the stronger the attractions between solute and solvent molecules, the greater the solubility. So the stronger the attraction when you have polar and polar, the more likely it'll dissolve. If you have nonpolar and nonpolar, now you have lots of dispersion forces working, and those could dissolve as well. So here's the first example. Polar dissolves polar. Here's a water molecule, draw that guy. Here's another water molecule, draw this guy. And then this is a methanol, a 1-carbon alcohol. And you can see that this guy right here has hydrogen bonding because it's got an H connected to FORN. Water always have hydrogen bonding because it's got an H connected to FORN. And this one right here has an H connected to an FORN as well. And so we end up with a dipole moment going from positive here to negative right here, from positive here to more negative out here. And then here in this area, we have a more positive area going to a more negative area here. So this negative part right here would attract to this positive part right here. So this would be one attraction. And this positive part would attract to this more negative part right here. And therefore, polar dissolves polar because we have two polar molecules that are asymmetrical and asymmetrical. And then those dissolve. And of course, there'd be lots more water molecules around, and there'd be lots more of these. But just to do, zoom in on a couple of them to help you see that like dissolves like. All right, here's the second example. This is a nonpolar water molecule. I'm sorry, a nonpolar molecule. 1, 2, 3, 4, 5 carbons. So it's called pentane. You can see it's perfectly symmetrical. If you could cut it any way, it would be symmetry every single direction. So nonpolar. And then here's another nonpolar molecule right here. This is a 2-carbon, so that'd be ethane. And once again, you could slice it any way, and it would be totally symmetrical as well. So nonpolar dissolves nonpolar because the only forces in here are London dispersion forces. The only forces in here are London dispersion forces. And so the LDFs, or the dispersion forces, will work between those two molecules right there to make those dissolve in one another. So the solvent-solute interaction that's important is that you have like dissolving like. And if you kind of look down further, you can see an example in like real life right here. Here's hexane, which should have one more carbon than this. And then here's water, and water of course would look like this. And water's polar, and hexane would be nonpolar. And you can see that hexane does not mix with water. The word immiscible means that it does not mix. It's immiscible. It's immixable with one another. So that's one example of two things that don't mix very well together. Here's an example of a couple of pieces that do mix well together. These are ethanol molecules that are bonded together. Ethanol, of course, has an OH right here and an OH right here, and so you have the hydrogen bond going on between the molecules. And then when ethanol is dissolved in water, you can see water molecules also are polar, and therefore they would have a hydrogen bond characteristic between the two. So since ethanol molecules have hydrogen bonds and water molecules have hydrogen bonds, now we have like dissolves like, and so those would dissolve in one another because they have similar characteristics. Here's one more example. Here is a molecular structure of cyclohexane. So cyclohexane has 1, 2, 3, 4, 5, 6 carbons in a circle, and then it just has all kinds of hydrogens off of it. If you slice it any which way, as long as it's in half, you find out it's totally nonpolar. So this nonpolar substance would probably dissolve in something like this, because this is also nonpolar and it would only have dispersion forces. Now, to make something like this soluble, you'd probably want to replace a whole bunch of the H's with like OH groups, OH groups, OH groups, OH groups, OH groups. And then when you have lots of those, now you have hydrogen bonding that could take place at every one of these spots right here, and then it would be attracted to something like water. So, general rule once again, polar dissolves polar, nonpolar dissolves nonpolar. Opposites do not make a solution. So here is benzene. Benzene, of course, is a 6-carbon ring, and remember it has that resonating double bond that goes around here. And then I drew a bunch of water molecules around here, and water molecules, of course, are polar. And so the nonpolar substance would be perfectly symmetrical if you had to cut it every single way. That would not dissolve in water because water only has polarity to it and would have hydrogen bonding. So this would not dissolve in one another because opposites don't attract in this case. They've got to have the same kind. So how do you decide if it'll dissolve or not? Well, you can ask yourself 2 simple questions. Question number 1, draw the Lewis dot structure and ask, is it polar? Okay, does it have a dipole moment? Is it asymmetrical? After you draw the Lewis dot structure, asymmetry. Okay, check to see if it does. All right, draw the Lewis dot structure of the second item that you want to know if it dissolves in or not. Does it have the same characteristics? Is it polar? Is it asymmetrical? Or is it different? Is it perfectly symmetrical or is it nonpolar? Well, remember, like dissolves like, and so look for similar or like intermolecular forces and look for similar molecular mass. Similar intermolecular forces and similar molecular mass. Those are the 2 factors that help affect solubility. All right, a couple of real-world examples here. On the next page, we have 2 vitamins. All right. In a general rule, vitamins C and B are known as water-soluble vitamins, and vitamins A, D, E, and K are called fat-soluble vitamins. Now, water-soluble vitamins, the reason they're water-soluble is because they have lots of polar parts to their molecules. If you look at vitamin C, in this case, it has OH, 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 and OH. Lots of areas there, lots of areas there where we would have hydrogen bonding characteristics available. Let me see if I can get back to that spot here. I'm going to have to get lucky to get back there. We'll get there in a second. There we go. Whereas, like vitamin A, D, E, and K, those are mostly nonpolar. And so here's vitamin A, and you can see vitamin A has mostly a molecule that's nonpolar. Lots of C's and H's. Slice it, asymmetric, so totally symmetrical, symmetrical. But then it's got this one spot right here that could end up interacting with water, but only one versus a big, huge molecule right here that's mostly nonpolar. Well, remember, like dissolves like, and so if this thing's mostly nonpolar, it's not going to dissolve in something that's polar, like water. That's why they call this fat-soluble, because fat-soluble fats are nonpolar, and like dissolves like. This would dissolve in water, and therefore it is a water-soluble vitamin. All right, so note vitamin A right here, mostly nonpolar. Note vitamin C's got lots of OH groups. Lots of nonpolar parts here to the vitamin A, lots of polar parts here for the vitamin D. For the vitamin C. All right, one last thing. Let's take a look at predicting the solubility of some substances. Let's look at sample exercise 13.1 here. It says, predict whether each of the following substances is more likely to be dissolved in the nonpolar solvent carbon tetrachloride or in water. And then they give us a list of 4 different things. Well, I'm going to write those 4 different things down here, and then we're going to take a look and we're going to follow the patterns. And we're going to decide, will they dissolve better in CCl4 or in H2O? So first of all, you got to know something about each one of these. So when you draw carbon tetrachloride, you're going to get C with 4 Cl's around it, unshared pairs of electrons all around, and then ask yourself the question, is it symmetrical or not? Well, it doesn't matter which way you slice it. Which way you slice it, as long as you slice it in half, it's going to be perfectly symmetrical. So this is a nonpolar solvent. H2O, on the other hand, you already know this is bent, and we have a 104-degree bond angle right here, and then we know that there's these unshared pairs of electrons. They're going to be more negative, and this is going to be more positive, so this is a polar molecule. Well, remember, like dissolves like. So now when we go through each one of these, we have to decide, is it going to make positive and negative parts in its molecule, or is it going to be pretty symmetrical? Well, C7, H16, whoops, there's a 16 right there. This one is going to have 1, 2, 3, 4, 5, 6, 7 carbons in a row, and then off of each one of the carbons right here, we're going to have hydrogens. And if you look at it in the big scheme of things, we have lots and lots of very normal repeating patterns. Slice it in half, it's the same on both sides. Slice it in half, it's the same on both sides. Slice it in half, same. So this one is nonpolar. And so a nonpolar substance would dissolve in nonpolar substance, so this one would dissolve best in CCl4. So look back, how did I solve that? I solved it by first finding out whether this substance and this substance were polar or not, and then I took a look at the substance that they wanted to know if it was dissolved in. I drew the Lewis dot structure. I found out whether it was symmetrical or not. Those are your steps in deciding it. Na2SO4, well, this got a metal in it and a nonmetal, so this is going to be Na pluses, 2 of them, and SO4, 2 minuses. Then we're going to have positive and negative things here. These are ionic. Remember, ionic occurs when you have a metal and some nonmetals. And ionic things, of course, are positive and negative, and that's going to dissolve in things that have positives and negatives. This one, of course, has no positives and negatives. It's very nonpolar. Whereas water, oh my gosh, lots of positive, lots of negative to the molecule right here. And so the O minus area right here would go around the Na plus, and the positive H area would go around the SO4 2 minus. So this would be much more soluble in H2O. So notice how I recognized that it was ions. Okay, and it would break up into those 2 parts. HCl, draw the Lewis electron dot structure for that. Well, there's going to be a negative area right here, a positive area right here, because chlorine's a little more electronegative than hydrogen. Well, this dipole moment then would be attracted to something with a dipole moment. Well, that would be H2O again, of course, and so the positive would attract to the negative, and the negative would attract to the positive, so this would dissolve best in H2O again. Last one, I2, draw the Lewis electron dot structure. We get a perfectly symmetrical animal right here. Slice it any different way, and it's symmetrical. There's no buildup of electron charge in one place or the other. Only London dispersion forces inside of this one. Like dissolves like, it should want to dissolve in a nonpolar thing. Our nonpolar item right here is CCl4, so that's what it would dissolve the best in. All right, good luck in checking your solubilities and predicting those patterns.